Hi, it's Matt, and in this video we're going to talk about how to construct the Hamiltonian matrix. So in quantum mechanics, again, operators are going to be represented as matrices. The Hamiltonian is an operator, therefore it will be represented as a matrix. So the Hamiltonian matrix will have the form H is equal to, then a matrix of what we're going to call Hamiltonian matrix elements. The top left, for example, will be H11, where the first one represents the row and the second one represents the column. And then here we have H12, again, row 1, column 2. And each of these matrix elements is going to be given by Hij is equal to chi Hamiltonian operator chi j. So we'll discuss in a little bit later the full meaning of the bracket notation and how we would use it to get matrix elements. But for now, the Hamiltonian matrix can be written as the following. So instead of H11, H12, H21, etc., we could expand those out and for each place in the matrix, write the bracket integral that represents it. So for example, in row 2, column 1, here we would have H21, which is equivalent to the integral of chi2 Hamiltonian operator chi1. And remember that this is symmetric about the diagonal, so if I draw a line down the long diagonal, corresponding elements on each side will be equal. So for example, chi2 Hamiltonian chi1 here will be equal to chi1 Hamiltonian chi2 here. And that's just what this is saying here, but instead of numbers, I used I and j to make it general. So now let's do an example of this. So how do we put together the Hamiltonian matrix when we're given the matrix elements? So we're going to build the Hamiltonian matrix for three basis functions, chi1, chi2, chi3, and we're given the following information. I'm not going to read these all out, but we're essentially given chi1 Hamiltonian chi1, and so on. So the first thing that we're going to want to do given these elements, since we have three basis functions, we know we're going to need a 3 by 3 matrix. So I'm going to start by drawing that out. So now let's look at the first piece. We're given chi1 Hamiltonian chi1. So in this case, I is equal to 1 and j is equal to 1. Therefore, this is representative of the H11 element, or our top left element. I'm not going to write it with the decimals or the units right now, so I'm just going to put a 0. Now let's look at the next one. We have chi2 Hamiltonian chi2. Here we would have that I is equal to 2 and j is equal to 2. Therefore, this is representative of the H22 element. So that would be row 2, column 2. So that would be the center of our matrix here. So I'll put a negative 2.5. And then finally, the third one we're given is chi3 Hamiltonian chi3. At this point, I'm not going to fully write out the I and j, but here we can see they're both equal to 3. So this tells us that in row 3, column 3, our matrix element is negative 4.5. Now let's look at the next matrix element. We have chi1 Hamiltonian chi2. So here we're given that I is equal to 1 and j is equal to 2. So that means in row 1, column 2, we have a negative 1.0. However, we get additional information here, because remember that we're symmetric about the long diagonal. So we have, remember that's chi Hamiltonian chi j is equal to chi j Hamiltonian chi I. So what this means is that if I equals 1 and j equals 2, as in this case, that matrix element is negative 1, we could flip I and j, and that would be the same element. So just as row 1, column 2 is negative 1, row 2, column 1 would also be negative 1. Now let's look at the next one. We have chi1 Hamiltonian chi3. So that tells us that row 1, element 3 is negative 0.3. And then by symmetry, if that means that chi3 Hamiltonian chi1, or row 3, column 1, also needs to be negative 0.3. And finally, we're given chi2 Hamiltonian chi3. So that tells us that in row 2, column 3, we have negative 2.7. And similarly, we could flip the value of I and j, and we could get that in row 3, column 2, we also have negative 2.7. So in this case, this matrix here will be our Hamiltonian matrix for the given information. But now, sometimes we may not be given the matrix elements, and instead we may have to find them. And when that's not the case, we're going to have to manually compute the integrals. And to do that, we're going to remember the meaning of the bracket notation. So the bracket integral of chi1 Hamiltonian chi j is equivalent to the integral of chi1 conjugate. I didn't write the conjugate here because typically our basis functions will always be real, but technically we could have the conjugate there. And then the Hamiltonian operator applied to chi2, and then d tau. And this would be the integral across all space. And here, the Hamiltonian, so h hat, will be our standard Hamiltonian operator, and that will depend on what dimension we're in. So for example, in one dimension, we'll call that dimension x. Our Hamiltonian operator is negative h bar squared over 2m at times the second derivative with respect to x. So the bracket integral chi I Hamiltonian chi j, when I equals 1 and j equals 2, will be chi1 times negative h bar squared over 2m times the second derivative of chi2 dx. And again, here I'm assuming that chi1 is a real valued function. So now let's try an example of this. So here we're given the basis functions, and we need to compute the integrals manually. So here we're told that we have chi1 is going to be sine x from 0 to pi over 2, and chi2 will be cosine x from 0 to pi over 2, and they're going to be 0 elsewhere. Just as a disclaimer, I'm not saying these are good basis functions in quantum mechanics or even quantum mechanically allowed. I'm just using them here as examples because the integrals here will be pretty simple to compute. So here I just copied our basis functions onto this slide, and now we're going to compute the integrals. Just as a note, I'm not going to really explain how I'm computing the integrals here, and I'm just going to use an integral solver. If you have any questions on how they would be solved, feel free to comment them below and I'll answer them. But here I really want to focus on how we would find the elements, and less so the nitty-gritty of evaluating the integrals. So since we have two basis functions, we know that our operator matrices will be 2 by 2, meaning we're going to need 4 elements, the first of which being h11. And in bracket form, h11 we know is going to be chi1 Hamiltonian chi1, which expanded with integrals will be the integral from 0 to pi over 2, times we're now going to plug in chi1, which is sine of x. We're going to plug in our Hamiltonian, which is negative h bar squared over 2m times the second derivative. And we're going to apply that second derivative to chi1, which again is sine of x. And we're going to have a dx. Plugging this into an integral solver, what we end up finding is that this is h bar squared pi over 8m. So that's our top left element. Next, we need to find our second element, so row 1, column 2. So that's going to be h12. And in bracket notation, we're going to find this with chi1 Hamiltonian chi2. And this is going to be equal to the integral from 0 to pi over 2. Again, these are our bounds because the wave function is 0 outside of this, so we don't need to consider it. So again, we're going to be integrating. We're going to plug in chi1, which is sine of x, times our Hamiltonian, which is negative h bar squared over 2m, times the second derivative. And that second derivative is going to be applied to chi2, which we're given as cosine x dx. And plugging this into an integral calculator, we're going to get that this is h bar squared over 4m. Okay. Moving on to h21, at this point we're probably getting pretty tired if you're doing this as a question of evaluating integrals, and what's good is we could kind of skip this one, because due to symmetry we previously said that if we switch I and j, the value should be the same. So h21 is going to be equal to h12, which is going to be equal to h bar squared over 4m. So good. we now just have one more element defined, and that's our row 2, column 2, or our H22 element. And that in bracket form is going to be chi2 times the Hamiltonian applied to chi2. And now in integral form, this is going to be integral from 0 to pi over 2. We're then going to plug in chi2, which is cos of x, times negative h bar squared over 2m d squared dx squared, again our Hamiltonian, and then again apply to chi2, which we know is going to be cosine of x dx. Plugging this into an integral calculator, what we're left with is h bar squared pi over 8m. Just a note, I know h11 and h22 are equal here. That is not always going to be the case, and that happened just by coincidence with the functions I chose. So good, now that we have our 4 functions, we now just need to arrange them in a 2x2 matrix. And I'll write our final Hamiltonian matrix here in this nice yellow. So h11 is going to be row 1, column 1. So that's going to be h bar squared pi over 8m. Next, h12 is going to be row 1, column 2. And that's going to be h bar squared over 4m. Next, we're going to look at h21, which is going to be row 2, column 1. And that's going to be h bar squared over 4m. And finally, we have h22, which is going to be row 2, column 2. And that's going to be h bar squared pi over 8m. So here we have our full 2x2 Hamiltonian matrix, and that is what we have written in yellow.